Did anyone do this homework, the lunch exercise? Yeah? Can the energy increase? I mean, check what this rule, I'm actually going to still leave it as an exercise, and we can talk about it tomorrow. But notice the rule that we have here for, we have this rule for learning. These are the two rules of how the neuron acts. Basically, the neuron only acts when, let's call this quantity BI. I will argue that when BI goes up, the rate of change of V can only go up and or stay at the same. And that if BI becomes negative, so VI also decreases. And so that's still this argument. And therefore, it must be that DE, or let's rather say E, decreases. Okay? I'll make the slides available today. And but essentially, you fire when this guy is greater than UI. That's essentially the rule that we have here. And so then the voltage can increase, can be positive. If that goes down to be negative, then that also, if BI goes down, then the rate of DVI is also down. So they're either both negative or both positive. And as a result, the change of the energy is always down. And so the energy decreases. And that's what a Hopfield network is about. That you can have all these new units doing random things, flipping coins. I didn't get my quarter back, by the way. I noticed that at lunch when I had to give someone 20 cents. But we do get this emergent behavior, which is energy. And that emergent behavior is that if you have these units flipping this way, you guarantee that the energy of the system is actually going down. So you're getting into an attractor. To demonstrate what an attractor is, I need someone who's happy to volunteer their phone number. Any volunteers? Okay, so can you say your telephone number loud, quickly?
Right now?
Yeah.
609-751-1794.
Say it backwards.
4971-157-906.
Thank you. Good sport. Let's give him a... He's remembered the sequence of numbers forward. That's an associative memory. It's the sort of thing we've been hearing a lot about. That's an attractor. It's a low energy state. At least that's how John Hopfield would see it. You can take this to the continuous world. In other words, you can now introduce, instead of having a gate mechanism, you introduce a sigmoid. So you have this sigmoid transformation, the usual 1 over 1 plus e to the minus x. And you can now describe the voltage of the neuron, just using linear systems, as a function of the current, and as a function of properties of the neuron, like the membrane capacity, the delay in transmission of the spike, because we saw those drawings yesterday that the spike is not just deterministic like spikes, but it's actually these physical systems with delay. In terms of the impedance, at the end of the day, it's just a chemical, electrochemical process. And I don't mean for you to go and understand differential equations. If you've never seen one in your life, you will not get it from this. But I do hope you go to the Wikipedia page and you Google RC circuit wiki, because this resistor capacitor circuit, that's the model of a neuron that corresponds to, together with this nonlinear transformation, that's essentially one of the most popular models out there. So the neuron is modeled in this way as a dynamical system, and so each neuron is a linear differential equation with a forcing term. This is sort of for the engineers out there. And if you have a linear differential equation with a forcing term, it's easy to solve. If you have a system, things start getting more complicated, but essentially that's what we have in these models. They are systems of differential equations. If you give it the Boltzmann energy, in this case now there's a continuous bias, but if you give the Boltzmann energy and this is part 2 of the exercise, you do a little bit of math, or you cheat by Googling John Hopfield's papers, you'll find that the energy also is guaranteed to decrease. Okay, so you have all these neurons doing their own thing, but they're actually finding attractors. So the sort of picture is more or less like this. Whatever state you encounter a neuron in, that neuron will go down to an equilibrium point. And there's multiple equilibrium points, and this is what John argues are memories. Now, long time ago, and I just got this figure out of Google Images, like, don't do this at home. I shouldn't do this with a camera. I couldn't get the source, but I would love to actually go and find out the source. Because a while ago, people were already playing with these type of self-organizing maps, the topographic maps that we've seen already a few times this week. And then they're putting other layers, but in this case, I guess, trying to build associative memories. So this is essentially a Hopfield net where each unit is implementing a simple ODE, and that has this behavior, that it has these attractors. Your phone number resides here, and you can recall it because it's in that basin, but you don't have a basin for your phone number backward, or the alphabet backward, or many other things. If you assign a unit to the image, then Hopfield had this, actually I don't know who did this work either, but the people who played with Hopfield networks many decades ago were able to do this. And I imagine this is because this was the resolution of their computer screens. But it does a pretty good job at solving a problem that currently we find hard to do with our own machines. It also solves another very hard perceptual problem, the completion. So if you haven't seen Hopfield networks, I strongly recommend you go and look at that literature. And then the message to get here is that modeling things with systems of differential equations is something to be thinking about, because after all, the brain's a dynamical system, and a lot of things out there in nature are dynamical systems. At the same time as someone who's worked with linear systems and nonlinear differential equations, it's extremely hard to do this. This type of modeling gets soon very unwieldy and very hard. It becomes very intractable. Nonetheless, I do think it's important to keep in mind that our algorithms are actually sort of discretizations of these continuous systems, because I think there is something to benefit from knowing that. One of the things you can benefit from is that if you know that, you can talk about the convergence of algorithms, as we'll see in the next example. So stochastic approximation. So you've already been introduced to it, I believe, but I'm just going to give you sort of a quick intro to it, because it will relate to the rest of the talk when we go and talk about things like maximum likelihood and CD and so on. So imagine we have the following setting. We want to maximize some function, or minimize the function. And let's say that the function that we're minimizing, let's say I'm going to call it h of theta, and I'm going to assume that that function is also a function of a random variable. So the random variable x has a distribution. And my goal is to minimize this expression of a theta. Okay. Now this happens a lot in learning. These are the hidden units. We don't. The x's are typically the hidden units. We don't observe them, and so we need to marginalize them, integrate out over the hidden variables. Now, but the problem is much more general, and in fact, the RL problem, the control problem, can also be written in this form. Loosely, I'm going to assume that all these integrals are regular, etc., etc. And what I'm going to do is I'm going to define this function j of theta. Well, first I'll call this guy h of theta. And if it was a large discrete integral, it would be the same thing. It would be just a big sum. And I'm going to assume that everything is regular so that I can actually swap the sum with the derivative and write this as in this form. Okay. My p doesn't depend on theta. Sometimes in control the p depends on theta and the problem is harder. And what do we do when we do learning? We equate the gradient to 0. Okay, so we go down and we find a place where the derivative is 0. Now, if I take this equation, grad j of theta, and I equate it to 0, I'm going to do the following trick. I'm going to multiply both sides by alpha, where alpha is a constant. I'll soon say what alpha has to be. And I'm going to add theta to both sides. Okay. And then the last thing I'm going to do, and this unfortunately I have to go to the next page. So I have theta plus alpha j theta equal theta. So let me rewrite it here. Okay. Now the problem is I don't have the gradient because to have the gradient I need to integrate over this expression. Okay, so and this I'm assuming is a very high dimensional integral or an exponential sum, so it's intractable. However, I can do the Monte Carlo thing. I can draw a bunch of samples from, if I draw a bunch of samples from P of x, so I draw samples I from P of x, then I can approximate the gradient. Let's assume I draw capital N samples. Okay, so that's the Monte Carlo that Ian taught us this morning. If I draw samples from P, this is basically the expectation of the gradient of this augmented function. And if I do take samples from P, I can approximate the expectation with the empirical average. Okay, so it's essential thing that we do all the time. We always do averages this way, but we know by the law of large numbers that as n goes to infinity, you approximate this for a given theta. Okay, so we can approximate it that way. And so what I can do now is I can discretize this equation. And the way I'll discretize it, I'm going to call this theta t plus 1. This is going to be theta t minus alpha. And then I will have here 1 over n, sum from I equal 1 to n, grad j of theta x, I don't know, maybe from xt minus n. Let me just call it xi for simplicity. Oh, I made a mistake there. Thank you. Okay, so I'm just replacing the gradient by its Monte Carlo estimate. Okay, so I can do that, but it turns out that I can actually, okay, so let me do one more thing. So I've done this. And I will first argue that I can actually do this by drawing only one sample. Okay. Just one sample will be enough, and I'll soon argue why that is the case. But let's assume for now that I only draw one sample. Then what I can do also to this expression, so that's a very bad Monte Carlo estimate, but because we keep updating theta, I'm actually not just drawing one sample, but every time I update theta, I'm adding a new sample. So the intuition is that when I have a bad theta, it doesn't, at the beginning, it doesn't make sense to draw too many samples at the beginning because my theta is not very good anyway, so why should I waste effort? I should maybe just draw samples as I go with my theta. And I'll soon give you another intuition for why that would be fine. But let's now take this, and what I'm going to do is I'm going to subtract grad j of theta, and I'm going to add grad j of theta. And I'm purposely grouping the terms this way. Okay. Now, this is the equation that we want, the gradient descent equation, the equation that says that theta moves in the direction of the gradient. This is the difference between the gradient and its Monte Carlo estimate using one sample. Okay, so this is the error in the gradient. And the noise in stochastic gradient descent doesn't arise because we're adding noise to the gradient. The noise arises because we can't see the entire world. We don't see the whole data. We only have partial observability. Now, what you would want is this noise to vanish, okay, asymptotically as your theta gets updated. So we can make alpha something that goes down to 0 to ensure that this noise vanishes. But we can't make alpha go down to 0 too quickly because then you don't follow the gradient. So there's a sort of a trade-off. Okay? And so what people typically do is they use alpha equal to 1 over t. And the reason they use 1 over t, many other things are possible, but 1 over t is the thing that's the easiest to prove things with, because the sum of 1 over t tends to infinity. That's a harmonic series, whereas the sum of a 1 of t squared, which is related to the variance of the noise, is finite. And for the people who've done statistics, if the variance is finite, you can control the variance, you can control via Chebyshev and Borel-Cantelli the probability of deviation, you can prove that this vanishes. And because 1 over t goes to infinity, that means you have the opportunity to visit the whole space. That's basically, in a nutshell, the argument of how you would prove convergence of maximum likelihood, stochastic maximum likelihood, or any stochastic descent that is optimizing this objective. I still haven't defined what the likelihood is, but I'll do that soon. Now, what we can also do is, assuming that the error vanishes, we can now do the opposite of what I did up on this sheet of paper. I can do the opposite of discretizing. And I basically move the theta t to the other side. And I write this as an ODE. And when we're trying to prove convergence, we write it as an ODE, and we show that this ODE is actually convergent. That this ODE actually goes down as like e to the minus, whatever the usual thing. Okay. So to analyze the convergence of the algorithms that we use, like CD, algorithms like stochastic maximum likelihood, and so on, it's really useful to know differential equations because, again, they give us, that's a very common method of proof. Borkar has an excellent book on this, on stochastic approximation, and that's where what you would need to sort of read to do theory and how these algorithms converge. And that's essentially what Laurent used when he proved convergence of what is now known as persistent maximum persistent CD.
What modifications would you have to make if p depends on theta?
Oh, okay. So it gets really interesting. Can I take this one offline? But basically, there's a bunch of other methods that we play with, IPA. It gets really interesting because there's more than one way of doing it. So in control, you need to worry about that. Here we don't. No, here sometimes we do actually, but this advanced topic. Okay, so the differential equations help us, and because we're iterating, we're essentially we're drawing actually not just one sample, we're drawing many samples, and so what we're using is essentially the weak law of large numbers. Let's see if I have space here. I'm going to write one more thing. This is the same as when you compute an expectation. If you have mu is equal to the sum of 1 over t, sum over t up to t, you can also, let's call it mu t. You can also write mu t as x, xt, the latest guy, plus 1 over t minus 1 times t minus 1 divided by t, and this would be 1 over t here, and then sum up to t minus 1 of t of xt. Sorry, I was running out of space there. And so you basically can write this as mu t is just equal to mu t minus 1 plus times 1 minus 1 over t, and then plus 1 over t x t. So you only need one sample in order to compute your mean, because you're maintaining the average here. And that's essentially the idea of why you only need one sample. Okay. And most RL algorithms, like Q-learning and so on, they're exactly the same thing. It's just a way of doing averages recursively. Okay, maximum likelihood, which is an application. Now we're going to get into how do we learn these models. And there's many ways to learn these models. And maybe just before we dive into more math, let's look at what different estimators do. So what I'm showing you here is a demo. This is the thing that I ask you guys to download. You can download this and you can play with this from Ben Marland's webpage. So Ben came up with this demo. And what it does is essentially it allows you to enter, to draw your own MNIST numbers to see if this thing will recognize. You can draw them with a pencil or a brush. You can add noise. You can use an eraser to erase stuff. Like I can go with the eraser and erase this bit, and hopefully now the 4 will become a 9, not so much. But maybe pseudo likelihood, oh, it works better. So you can change the estimators. So we can use ratio matching, which Apohivarian came up with. Pseudo likelihood by Julian Bisak, one of the most widely used estimators out there, especially with CRFs. CD, and the stochastic maximum likelihood algorithm. So there's different algorithms, and they all sort of behave differently. So let me try to draw another number here. Sorry, I'm doing this over, that's why I wanted to see if someone had MATLAB, because I'm doing this over my, this is my machine at UBC. All right, so in this case, the algorithm thinks it's a maximum likelihood thinks it's a 6. CD gets it right for this particular example. Pseudo likelihood gets it wrong, and ratio matching is far, And that's because probably that 3 is not centered. So let's do another one. So in one example, you would say CD works better. The nice thing with this, sorry, it's painful to draw, and I need to make sure it's in the middle of the box, because this is not position invariant. Anyway, now one estimator ratio matching, and estimators are the rules as to how we derive parameters from data. I'm not talking about algorithms. I'm not talking about tricks. I'm talking about the general rules that we use to learn. The principles underlying inference. So there's this one. This one is still off with the 4, doesn't like it. CD still does okay. And stochastic maximum likelihood does okay. And then we can erase things to try to maybe make it more like a 4. And we can see what happens with each estimator. The filters here, oh, by the way, I should have said, this is the reconstruction of the model. This is the world, this is the reconstruction, and these are the filters that are being used to do the reconstruction. And let's see what, well, pseudo likelihood is way off there. But let's do something. Let's start adding noise to the image. And we discover interesting things. Like estimators actually don't necessarily get, some don't get bad when you add noise. Some do become bad at generating, but still good at classification. So being able to generate and classify don't seem to be necessarily the same thing. Let's keep adding noise. Okay, now you would hope most of these methods fail. Some methods are actually very good with a lot of noise. And so we're going to take a detour and look at something called robust statistics. Okay? Because not all estimators are good in the absence of noise. Some estimators are more noise tolerant than others, and in fact some methods benefit of noise. And I think the importance of adding noise as a regularizer and so on is something that Jeff already discussed a couple weeks ago here. But anyway, different estimators do everything, and even when we play with them, it's not entirely clear what it is that they're doing. Let's erase stuff. Okay, so we need to have a better understanding of what these different techniques that people keep proposing in the literature are doing. And that's essentially what the rest of the lecture today will be about. That's the motivation for it. All right, maximum likelihood. So maximum likelihood is a learning principle. It's very popular. People often say, oh, we learn the parameters by maximum likelihood. And what they mean by that, I think, is we learn them the right way. This is absolutely sound. And, you know, how could it go wrong? It's maximum likelihood. So we need to kind of first understand what maximum likelihood is. So I'm going to go over it quickly. A more in-depth study goes into things like sufficiency and so on, which you learn in a stats course in 4th year or so. Now, the idea of maximum likelihood, that's most frequently the way we see it presented, is you want to maximize the probability of the data given the parameters. In other words, you want to find the parameters that make this function simulate data that's very likely, that has higher probability. So you want to come up with a function that gives the data high probability. Maximum likelihood makes this important, is a frequentist technique. It assumes that the data has come from a model where there is a single truth. There is a true parameter, and we're after that true parameter. Okay? I will not talk much about Bayes until tomorrow at the end. Bayes will assume very different things, and you know, there are reasons why you would think of both techniques. Now let's look at maximum likelihood in sort of a bit more detail. Let's assume that your data is independent. In that case, if your data is independent, so there's no temporal dynamics or spatial dynamics, but you just have a bunch of digits, then the probability of the data factorizes as the product of all the probabilities. Logs are convex, so they don't change the position of the maximum, so we can do a log, and then log of a product becomes a sum of logs. And we often do logs because the probabilities have e's, and so this gets rid of the e. We can also add extra terms to this expression. We can multiply this by 1 over n, and we can add this because this doesn't depend on theta, so this doesn't change the position of the argmax. Okay, so I have a surface, and I'm just shifting up and down. I'm not changing the location of the optimum by shifting it. And then I can apply properties of logs. Now this is an average, and now I'm going to do the opposite. From the average, I'm going to go to the expectation. Now this expectation is well known in information theory. It's called the Kullback-Leibler divergence, or the entropy, relative entropy. And it's a way of measuring the, in quotation marks, the distance between the distribution, given that you know the truth, and the distribution for the parameter that you have. And the distributions are over the data. So in other words, it's measuring the distribution of the data simulated by the model and the distribution of, say, the data that was simulated by the ground truth. So what you can do, you can rewrite it like this. And so we'll see what we're doing is we're comparing a term that depends on the ground truth, p log p for the real world, so the truth. And then there is a p log p where the log is over the fantasized data of your model, which is essentially your brain here. Okay, p log p is a well-known, for the biologists on, it's a well-known technique in information theory. It's called the entropy, and it's a way of measuring uncertainty. If you have a coin and you're flipping a coin, if the coin is unbiased, the uncertainty is maximum because it could be heads or tails. And if you put a bit of lead on one side of the coin, then most of the time it falls heads. So the uncertainty, as you bias the coin toward B1, then the uncertainty goes down. So entropy is a measure of uncertainty. And essentially you can see that what we're doing is we're comparing the entropy of the data generated by the ground truth against, not quite the entropy, but something similar, but where the data in one of the terms has been generated by your model. So we're comparing statistics of the world against statistics of what you simulate in your head. If the two statistics match, you have found the maximum likelihood estimate. If what you imagine corresponds to what you see through this lens, then you have learned. So maximum likelihood fundamentally is a contrasting principle. But what you're doing is you're contrasting to, you're requiring know this truth, and you're requiring sum over all the possible data sets. So it's a bit intractable. Maximum likelihood is liked because of the following reasons. First, you can show, this is all equivalent, that, let's use this way of writing it, that as n goes to infinity, as your data set grows and you get more and more data points, your estimate, which often is denoted with a hat, will converge to the truth. That is, for any alpha, no matter how small this alpha is, the difference between these two guys goes to 0. The probability that they're different goes to 0. So, and we essentially call this consistency. It also has a property that follows from the central limit theorem, and is that the difference between the estimator and the truth is distributed according, as n goes to infinity, is distributed according to a normal distribution. There's a matrix here that is the second matrix of second derivatives of the objective. It's called the Fisher information matrix, and it's asymptotically unbiased. That is, the difference is 0. The mean is 0. So theta is really becoming theta naught. And so the question is, what is the variance? So in other words, sort of the caricature here would be something like, whoops. We have some ground truth, and as we go to infinity, you're converging to that. And so what you want to know is what is the variance of that estimator. So you might have an estimator like that, or you might have an estimator that does something slightly different, that has much less oscillation. And so they both asymptotically become unbiased, but one is oscillating more, so you want to find the one that has the lowest variance. Another result in statistics, and I strongly recommend a book by John Rice called Mathematical Statistics. It has all these results. It's an undergrad book used at Berkeley, so it's a very, very, very nice book. I use it often. And so another theorem in that book will tell you that this is the lowest variance that you can attain. And this is why we like maximum likelihood. Maximum likelihood converts to the truth, if there is a truth. And maximum likelihood also is out of all possible estimators, it attains the lowest variance. In other words, which is called the Cramer-Rao lower bound in statistics. So this seems nice, so we should just do maximum likelihood.
So there is no problem of local minima?
No, because you're dealing with the case here as your data is going to infinity. I'm going to point you out tomorrow to there's a very nice blog entry of Radford Neal on this, which has a nice demo that shows what happens to the distribution as you acquire more data.
Nando, related to this question, what happens if you have a fixed amount of data like this? So in that case, you may want to trade off variance
and bias. So we don't usually have, as Mark correctly pointed out, what I just described is an asymptotic result. It's as the data goes to infinity. In reality, no one, even Google, has infinity of data. And so what we do is, in the end, try to come up with finite samples intuitions that guide our design. So in computer science theory, we often use the type of Chernoff bounds, and then we bound the exponents, and we get VC dimensions, and we use covered lemmas to get even better results, and so on. But those still are kind of loose, even for finite sample sizes. In practice, you would also do bootstraps if you want to get confidence estimates of how well you're doing it. And the bootstrap is an excellent thing to know of. Another result that's very useful is the following. And I'm not going to prove it, but I'm just going to, essentially, a lot of you from talking to you have seen these results before, so I'm just going to mention them. But I decided to keep them in the slides because I thought these are sort of basics that I think everyone doing deep learning has to know. The bias is the expectation over all your data, and it's important to know that the estimator is a function of the data. The random variable here is the data, not theta, the data, because you haven't seen the whole data, so there's uncertainty in the data. The distribution is over the data. You're integrating with respect to the data. That's what the uncertainty is, because you don't have all the data. So your bias is the deviation between the estimator, the expected estimator, and the ground truth. How far is the average of? So if you had your estimator and you try it, imagine tying several data sets and you take the average, how far is that average from the ground truth? That gives you your systematic bias. And your variance is how much it is oscillating. So it's looking at essentially your estimator minus the average squared. Okay. Now, if you take the mean squared error, and there's a small result relating mean square error to weak convergence, which was what I described as consistency. And you get consistency if you can make the mean square error go to 0. And I just noticed a mistake here. And with a little bit of algebra, you can show that the mean square error, that is what you need to make vanish to 0, always has two components, bias and variance. Okay? So you can be far from the function. So you might have an estimator. Let's bring the picture again. So let's say the ground truth. So you might have an estimator that has 0 bias but very large variance. And you might have another estimator that has bias but low variance. Okay, so asymptotically would actually never attain the optimum. But the other one, the green guy, asymptotically will eventually converge to the absolute truth. But the other one is close enough to the truth when you have, what was the scalable problem? 10 million, let's say 1 billion images. Okay, so if you have 1 billion images, you might want an estimator that has some bias. And this is sort of the things that you have to trade off when dealing with this. Random forests is basically built upon these principles. It's how to deal with creating, in that case, is you create estimators that are unbiased, but they have huge variance, but then you average them to kill the variance. And it works extremely well. All right, so typically the way we do maximum likelihood is we have a probability distribution. Let's say if we have a Gaussian, we take the log, and then to get the maximum likelihood estimates, we just differentiate with respect to the quantity of interest. If I differentiate the Gaussian with respect to the mu, I get that the maximum likelihood estimate is the empirical mean. If I differentiate it with respect to sigma, I get the sample variance estimate. And this is the things that we refer to as sufficient statistics of the data. You can do the same thing for any probability distribution. You can do it for a coin flip distribution, from a Bernoulli distribution. You again differentiate it. You aggregate it over all the data. And when you differentiate, you get that the probability of, say, tails is number of tails divided by number of tails plus number of heads. So you get things that make sense intuitively. If you had something, and this again, I'm going very quickly over these slides. I'm going to leave these slides for, if you haven't done the sort of basic statistics, you can go over them at your own pace later on, because you'll have the slides. But the workings is always the same. You write a distribution, you then write the sum of the logs of all the terms. That gives you some cost function, and then we differentiate the cost function with respect to the parameters to give us our estimate. In the case of this distribution, the logistic distribution, you no longer have a tractable answer like we had before, so it's not closed form, but you do get an expression of the gradient. This is the cross entropy that's often used to train neural nets. You get an estimate of the gradient by doing that. If you take second derivatives, you get something called the Hessian, which is a matrix. So there's a vectors matrix. You can show that this is convex because this thing has positive curvature, and that guarantees that you can come up with very efficient algorithms for finding the optimum. And that's the definition of the gradient. It's just a vector of derivatives. A Hessian is a matrix of second derivatives. And so I'm only including these so that you can go over them late. I want to move back to deep learning. So that was a very quick detour into what maximum likelihood is. So it's a nice estimator. It has all these nice properties. With it come these intuitions of a bias and variance. But it also has its problems. So when you review a paper and says we did maximum likelihood, don't just jump in to believe that it's right, that maximum likelihood was this sort of divine objective. It's just one of many estimators with some nice properties and some problems. It's expensive to compute in some cases, as we will see. It can suffer from overfitting, so we need to bring in regularizers. Because like if you're doing k-means, you can often, if you do a mixture of Gaussians, you can often get the variance going to 0. That is, you get a cluster centered at a single point, and when you get a Gaussian in one single point, that Gaussian, the height goes to infinity, so it's giving you a hell of a lot of likelihood, but it's doing absolutely the wrong thing. It's a point estimate, and it does not give you a whole distribution, which gives you uncertainty estimates. And I think Ian made some very good reasons, outlined some very good reasons as to why sometimes we might want to go beyond point estimates. The other thing, as we saw, it might not be the best also way of handling data that might have, say, outliers and all of that. And we certainly saw in that example that as I added noise, maximum likelihood kind of got bad, and ratio matching was actually working quite well. And this is something that's been known in statistics for a long time. There's a whole class of estimators called M-estimators, which include maximum likelihood, but it also has other things like the Huber loss and so on, which allows you to handle outliers. Maximum likelihood is, however, used a lot, and because it has this property that it's consistent and it's efficient. And when I mean efficient, I mean statistically efficient. Statisticians by efficiency mean statistical efficiency. That is, asymptotically it converges to the right thing, and it's the one that has the lowest variance. But unfortunately, quite often in the problems that we have to deal with in deep learning, maximum likelihood is not a point here in the tractable space, but maximum likelihood is a point there. It's statistically efficient, but it's not, and it's consistent, but it's not tractable. So it converges to the truth. It has good asymptotic behavior, but it might have terms that are impossible to compute. Okay, it might have terms that are actually NP hard to solve for. And so to deal with this, people have proposed a numerous set of estimators. So Julian Bisag, he proposed the pseudo-likelihood method many years ago in Bayesian statistics. Ratio matching is a popular estimator for, and here I'm talking just about problems that have binary variables for the time being. So ratio matching applies to discrete distributions. It's a good one. Siwei Liu proposed generalized score matching a few years ago. Other folks from Appa's team have been proposing all these other estimators, and even people from Bruno's lab have also been proposing other estimators, and the list continues. Really, a lot of people keep coming up with new estimators. And what happens quite often is that there's not enough, I should have mentioned the CD and so on. And what happens is quite often there's not enough comparisons between these estimators, either empirically or theoretically. And I think it's important to get used to doing these comparisons, because otherwise we're kind of in the dark. We're just doing heuristics. And this is nothing, again, to do with algorithms. We haven't even gone down to the, I'm at the higher level of inference principle. So you're doing maximum likelihood, and then you can choose to do LBFGS or proximal gradients or stochastic coin flipping or whatever. This is independent of the algorithm. It's how we set up the problem, how we set up the learning problem. And so far, to revise, we've learned one thing. Maximum likelihood is contrasting the world against what's in my head. Okay? Now what I'll do is I'm going to use RBMs. And has someone covered RBMs in the course so far? Yeah. So okay, I'll go over it quick then. So that's an RBM. It has hidden units, binary, and I'm going to assume that this is a restricted binary RBM for the time being today. Tomorrow I'll do continuous models. Today I'm planning to do binary models. Oh, I have until 3:30?
Yeah.
Oh. Okay, I'm going to do this quickly, since you've seen RBMs before. So the RBMs have this pairwise energy, pairwise interactions and biases, and then you can compute their you have an expression for the probability. We saw this before. And you can compute the conditionals, so you can exactly get the probability of a node firing given all the other ones, because there's conditional independence in the graph. And the other thing you can do is you can sum over the hidden units, because the hidden units are all independent, so you can actually sum over them, and you get an expression that doesn't involve any h's. And that expression is often called the free energy, so folks use an F. And you can do this with RBMs, but you can do this with MPOT models. You can do this with MC RBMs. A lot of the models, pretty much that we saw yesterday. So if you have these factored models, you can still do this. Now, so the nice thing about doing that is we get rid of the latent variable, so that we don't have this confounding term. However, we can't sum over x, because now these now are all dependent. But once you marginalize the hidden units, the visible units become all dependent. So there's a single click, and that is again an exponential sum. Stochastic maximum likelihood. What it does is it tries to, the objective of stochastic maximum likelihood is to, again, with respect to the empirical distribution of the data. So if you draw samples from this, what that means is if we draw samples xi from the distribution of the data, then this becomes 1 over n sum I equal 1 to n log p theta xi. So it's the distribution evaluated at data samples. If you take derivatives of this to find an expression for the gradient, which I hope someone covered, if not tomorrow or just after hours I can go over this with you, you get that the gradient looks like this. The gradient is contrasting the free energy evaluated at the data and the free energy, the expected free energy. Now we can't do the expectation, so what we do is we draw samples and we approximate this expectation with a few samples. But we've already seen that if we do this if we learn online, we don't need all the samples, we only need one sample. So stochastic maximum likelihood with one sample is essentially the algorithm I derived before. If you instead assume that, and so the way we draw the samples is by running a Markov chain. So we're basically doing alternating Gibbs sampling as we saw this morning. If instead of alternating Gibbs sampling, you just go to the data and you do a random perturbation of the data, you get an algorithm that is exactly the same as maximum likelihood. Like this looks the same. The only difference is that the samples are now not drawn from a Markov chain that's visiting the entire world, but the samples are being drawn just by perturbing the data. So when would this work? It would work when the distribution is very peaked, when you have a lot of data, because then if you just perturb the data, if you're very peaked, you're going to be changing the shape of the part of the space that matters near the data. If you have very little data, this is probably unlikely to do a good job. But note that computationally it's essentially the same as the other algorithm. I can draw n samples here, and then I would have exactly the same computation. Pseudo likelihood does something smart, which is it only considers one node at a time. So what it does is it's trying to it sums over all the nodes. Let's assume that we have d random variables, and it sums the conditionals one at a time. Okay, so it's just basically it's factored the distribution as a product of conditionals. And the update looks exactly the same as before, but now you need to sum over d. So you're summing over partitions, and this symbol means that I've only flipped the dth unit. So I have a vector, and in order to get the contrasting term, I flip one unit. Okay, so maximum likelihood does a random walk to do a random flip of units. CD looks at the data, does a random perturbation. Pseudo likelihood flips one unit, and it considers all possible flips. So it sums over all possible flips. Okay, and again, it's contrasting the free energy. The other estimators, basically, this is the bottom line. They're contrasting the same terms, except that they have weighting functions. These weighting functions is what makes some more robust to others. You can plot them, and you'll see that some have heavy tails, some don't have heavy tails, and that accounts for noise robustness. And then there's a bunch more. Here is the summary. Gradient for comparison of all these estimators. They all are contrasting the free energy. The only difference is what you're contrasting against. A sample, a perturbation of the data, flipping one variable at a time. But fundamentally, it's all about how do you pick the negative data. We saw some examples in natural language processing where you perturb your sentences, but the key thing is when we're learning, it's always important to think of what is your data and how could you come up with data, what kind of perturbations you could come up with so as to maximize the difference of the world against anything else other than the world. That's a sort of fundamental principle that is being used here. Tomorrow when I start, tomorrow there's going to be, I think I have to give 2 lectures still. So one will be on, can we now optimize this? Can we now find what is the best perturbation you could do here so as to learn as efficiently as possible? And so I'm going to go over some work of Ben Marlin that tries to address that question. By the way, Ben is probably watching this. Thanks for the slides. He prepared many of these. The other thing we will look at is what happens with continuous estimators. And we'll look at this thing called score matching. And we'll see that when I apply score matching to an RBM, I'm going to get an autoencoder. And it's going to be an autoencoder with a particular regularizer, which depends on the variance of projections of hidden units. When I apply score matching to a MCRBM or an MPOT, new autoencoders will arise. And so you can think of knowing these estimators allows you, these alternate estimators to maximum likelihood, allows you to design using probability, which is nice to glue things together. But then at the end, you get an autoencoder, which is very easy to optimize using our usual tricks. And then the last lecture in the afternoon is going to be more like the first lecture. So we don't have an afternoon lectures. The second lecture of the morning is going to be more like my first lecture today, which will be more like fun examples and how to use like RBMs for tracking and nice apps. Thank you.